Welcome to Theory of Computation. This is lecture number 21. We have started studying complexity theory. We are done with our study of computability theory and now we have moved on to a new topic. As you know, in computability theory, we ask the question which functions are computable or which languages are decidable. So if a language is decidable, that means we have an algorithm that decides that language. That language can be decided by a mechanical process, which we call an algorithm or a Turing machine. However, if somebody tells us that a language is decidable, they are not telling us how many resources will be required to solve that problem. For example, they're not saying how fast is that algorithm. They're just saying, I have an algorithm which solves this given problem. They are also not saying how much space the algorithm will require. Complexity theory looks at problems more closely. It takes a closer look at the problems. It does not ask for whether there is an algorithm to solve a problem or not, but it also asks what are the resources required to solve a given problem. So algorithms are analyzed much more delicately. You must have noticed that in the previous part of the course, whenever we wanted to prove that a problem was decidable, all we did was we produced a Turing machine or an algorithm that decides that problem. Then we went on to prove that the algorithm is correct. That means it accepts exactly the strings that are in the language and rejects all the strings that are not in the language. However, we never actually cared about how much time this algorithm takes or how much space this algorithm takes. So there may be many decidable problems which require extremely large amount of time and space to solve. If that is the case, although we have an algorithm to solve that problem, we do not have an efficient algorithm. What that means is, for all practical purposes, that problem is unsolvable on a computer. This is the view that complexity theory takes. So the goal of complexity theory is to identify problems that in some sense we can solve in practice. And it also tries to find out where is the threshold which makes problems intractable, not uncomputable, but intractable. A problem is intractable if it requires too many resources to solve. So complexity theory is a much more practical way of looking at problems. Complexity theory has been one of the most successful branches of computer science. On one hand, it has been extremely successful as we've been able to identify, in some sense, what makes a problem difficult to solve or what makes a problem general so that it cannot be solved on a computer fast. On the other hand, it has also been extremely unsuccessful branch of theoretical computer science because the kind of answers that we could give about computable problems, we do not have analogues of those theorems in complexity theory. It is a much younger field of computer science and it is a lot more active than computability theory, and it's a very modern field of computer science. So let us begin today's lecture. What we will do today is we will look at big O notation. After that, we have a brief look at little o notation. You have already studied these things in your previous courses, so we will do a quick review of those. Then we'll talk about time complexity classes. After that, we'll talk about non-deterministic Turing machines. And in the end, we will define the class P and have a small discussion on that. So, as you know, the big O notation is used to say something about a function. What we are interested in a function from integers to integers, and think of this function as the time taken by an algorithm to solve a certain problem. We're not really interested in this function completely. We're not interested in the whole detail of how this function looked like, because the function may be complicated and we may not be able to ever say anything meaningful about what exactly the function is. What we want to do is we want to look at the order of growth of that function. If we can find out the order of growth of this function, then what we can do is we can say how much more time the machine will take as we scale the problem. What will happen if we give it larger and larger inputs? What would happen to the time required? So for example, if we say a Turing machine runs in time order n squared, well, that tells me something very important. It says that every time I give it double the size of the problem, it will take 4 times more amount of time. And that's an intrinsic property of the time complexity of a Turing machine or an algorithm. On the other hand, computing it exactly may be very difficult. So now we will be looking at resource-bounded computations. The most important resources that we are going to look at is time and space. Let us start with this example. You have this language 0 to the k, 1 to the k, where k is greater than or equal to 0. We saw an algorithm that decides this language and runs in order n squared. Or we saw a one-tape Turing machine. Well, let's review quickly what that Turing machine was doing. You get your input, and what you want to know is if all the zeros come before all the ones, and if the number of zeros is equal to the number of ones in the input. Well, this machine can make one pass over its input and make sure that all the zeros come before ones, otherwise it can simply reject. Then the machine starts zigzagging through the input, going to the zeros, crossing one off, and then going to a 1 and crossing it off. It keeps doing that. If it runs out of zeros and there are ones present, then that means there were more ones on the tape. If it runs out of ones and there are zeros present, that means there are more zeros in the tape and it can reject. On the other hand, if it successfully crosses off all its input, then the number of zeros on the tape must be equal to the number of ones on the tape. So this is a very simple one-tape Turing machine that decides this language in time order n squared. The reason it takes time order n squared is, imagine that the input has n characters in it, then the machine makes passes. It will have to make n over 2 passes because it crosses off a 0 and a 1 in one pass. So it makes n over 2 passes over a tape of length n. So the total time required would be n over 2 times n, which is order n squared. Well, what we have done now is something different than what we were doing in computability theory. In computability theory, we would have just said that this language is decidable. We have a decider for it. This algorithm takes finite amount of time, and therefore it decides the language, and the question was answered. Well, complexity theory says, well, how much time does this algorithm take? And the answer is order n squared. Now we can ask another question. Can we design a better algorithm which decides this language? Can we come up with a different Turing machine which decides this language in less time? In order to do that, we'll have to develop some notation. Let's say that you have two functions f and g which map natural numbers to r. Recall that f is big O of g of n if there is a positive integer c and n naught, such that for all n greater than n naught, f of n is bounded by c times g of n. In this case, we say gn is an asymptotic upper bound for f. Sometimes we will just say that g is an upper bound for f. Whenever I say that, it would mean it's an asymptotic upper bound. So the big O notation, you should imagine it like this. F is a complicated function that you cannot completely understand, or you cannot get a formula for it. And g is a very simple function that you understand. For example, it's n or n squared or n cubed, or it may be n log n. When you say f is big O of g, what you're saying is f, when you scale n, f scales as much as g does, not more than that. So what you're doing is you're giving a meaningful, simpler upper bound for f. So as an example, f of n is equal to 13n to the 4 plus 7n squared plus 13. Well, in this case, you know that n to the 4 grows much faster than n squared. So really this function, the bulk of the function comes from the n to the 4 terms. So if we ignore constants, we will be able to say that this function is order n to the 4. This function is also order n to the 5 because it can also be upper bounded by some constant times n to the 5. However, this function is not order n to the cube. It grows faster than n cubed. You cannot put a constant in front of n cubed and bound this function. It may seem strange that this function is order n to the 4 and it is also order n to the 5. Well, remember, we're just saying that G is an asymptotic upper bound on F. So an upper bound, if F is bounded by one upper bound and you take that upper bound's upper bound, you will get another upper bound for F. That is just very simple. What we are saying is that not that G is a tight upper bound for F. We're saying that F is an upper bound, asymptotic upper bound for G. It may not be tight. Another example is if f of n is log to the base b of n, where b is any constant, then we can write log to the base b of n as log to the base 2 of n over log to the base b. Now log to the base 2 of b is a constant. Hence, f of n is order log n. So if you have the function log to the base 500 of n, well, that's also order log of n, where we computer scientists always take the log to be in base 2. So logs under any base are immune to in terms of order of growth. They can be bounded by log to the base 2 of n. Another function is 5n log n plus 200n log n plus 17. And this function is order n log n. This is because log n grows much slower than log n. So the first term dominates even though the constant attached to the second term seems to be larger. If you go through the definition of big O notation, once again you will see very easily that f of n is big O of n log n. We can use the big O notation in exponents also. Thus, 2 to the order n stands for a function that is upper bounded by 2 to the cn for some constant c. We have to be careful. So, for example, what does 2 to the big O of log n mean? What would 2 to the big O of log n mean? If you do it very quickly without thinking about the definition of big O notation, you'll say, well, 2 to the log n is n. So this function is order n. Well, that is incorrect. Because remember, order n actually denotes some function which can be bounded by c times log n, where c is a constant. So what you actually get is 2 to the c times log n. Now the c is there in the exponent. So this whole thing becomes n to the c. So 2 to the order log n denotes all functions of the form n to the c, where c is a constant. So 2 to the order log n, in other words, denotes functions which can be bounded by a polynomial. Bounds of the form n to the c will be called polynomial bounds, whereas bounds of the form 2 to the n to the c are called exponential bounds. So polynomial bounds are what we are going to think of as reasonable bounds. So we can spend that much time on a problem practically. This is what is going to be our definition of what is practical or reasonable amount of time. On the other hand, exponential bounds, well, we are going to consider them too large. We would say that if we have an algorithm that takes exponential time, then it's taking too much time. It's not a practical algorithm. I would remind you that between polynomial and exponential, there are a lot of other functions. So there can be algorithms that take what is called pseudo-polynomial time, or which is somewhere in between polynomial and exponential time. We would also consider those algorithms unpractical, but they would be better than exponential time algorithms. Well, now let's look at the small o notation. Big O notation roughly says that f is asymptotically upper bounded by g. Now what we want to say is f grows strictly slower than g. Well, the definition is simple enough. Suppose you have two functions which map natural numbers to the reals, to the positive part of the reals, then we'll say that fn is little o of g of n if the limit of the ratio fn over gn goes to 0. So the ratio of f and g becomes closer and closer to 0 as n goes to infinity. In this case, f over g is going to 0. What that means is f is not growing as fast as g. It's growing strictly slower than g, and that too in terms of that you cannot bound f over g by any constant. That constant will keep dropping. So suppose f was the time taken by my algorithm and g was the time taken by your algorithm. Then we can take the ratio f over g to find out whose algorithm is faster. So suppose f over g came out to be a half, then I could say that my algorithm is taking 50% of the time that your algorithm was taking. If the ratio f over g came out to be a quarter, I could say my algorithm was 4 times faster than yours. But if f over g comes out to be 0 in the limit, then I can say that as we give it larger and larger inputs, my algorithm will outperform your algorithm by as many times as you want. That is, the ratio of the time taken by the first algorithm versus the second algorithm goes to 0. So in some sense, the second algorithm is infinitely many times better than the first algorithm. Well, that's putting it in a very different way. Well, what we can say that this algorithm is a true algorithmic improvement over the first algorithm, in the sense that it's truly faster as you scale the problem, as you give it larger and larger inputs, it starts taking lesser and lesser time than its competing algorithm. A few things to notice, for example, is that the function square root of n is little o of n. Well, square root of n over n will be 1 over square root of n, and that limit goes to 0. N is little o of n log n, because if you take the ratio, that is 1 over log n, and as n goes to infinity, 1 over log n goes to 0. N log n is little o of n log n. In this case, if you take the ratio, you have log n over log n, and this limit as n goes to infinity also goes to 0. The next example, we have the function n log and n squared. N log n is little o of n squared because if you take the ratio, you get log of n over n, and as limit of n goes to infinity, this ratio goes to 0. The last example is the simplest one. It says that n squared is little o of n cubed. In this case, the ratio is 1 over n, and 1 over n goes to 0 as n goes to infinity. So when we say that f is little o of n, in some sense we're saying f is asymptotically strictly below g. Let's now look at a new Turing machine that recognizes the language for which we made this simple Turing machine. See, our previous Turing machine took time order n squared. So a very interesting question, and this is a question that complexity theory asks, is there another Turing machine, a better algorithm? Well, that algorithm has to solve this problem, but it has to do it faster. So we're looking for a Turing machine that recognizes this language in little o of n squared time. Anything faster than n squared would be considered an algorithmic improvement. Is there such a Turing machine? We have to design a single tape Turing machine that solves the same problem but does it faster. Well, it turns out that we can solve this problem faster. Let's look at that algorithm. What this algorithm will do is it'll scan the tape and make sure all the zeros are before ones. And this will now repeat itself as long as there are zeros and ones on the tape. It'll scan the tape, and if the total number of zeros and ones is odd, it would reject. Then it will scan and cross off every other zero, and it'll do the same with every other one. after repeating this, if all the zeros and ones are crossed out, then the machine would accept. Thus, for example, if we have 13 zeros, since this machine is crossing off every other zero, in the next stage there would be 6. So let's think a bit about how this Turing machine works. Let's say that the input happens to be 13 zeros followed by 13 ones. So it'll make sure all the zeros come before the ones, and that part is very simple. The machine will succeed, and now it'll start repeating itself. Remember, there are 13 zeros, and the machine is crossing off every other zero. So it would cross off 7 of them. In general, if there are 2r plus 1 zeros and it crosses off each alternative one, there'll be r zeros that will remain on the tape. If there are exactly 2r, which is an even number of zeros on the tape, and it crosses off every second one of them, it will once again have exactly r zeros on the tape. So if we observe, the number of zeros on the tape will start from 13, it'll go down to 6, and then when it crosses off every other zero in the next phase, it'll go down to 3, and then when it crosses off every other zero in the next phase, it'll go down to 1, and then there'll be just 1 0 and 1 1 left, and it'll see that the number is equal and therefore accept. So this Turing machine is accepting all the strings in which the number of zeros is equal to the number of ones. How much time does this Turing machine take? If there are total n zeros to begin with, every pass of this Turing machine is halving it. Thus, it will make only log n passes over its input. So the total time required to solve this problem using this Turing machine will be order n log n. Now we know that n log n is little o of n squared. So this points to a real algorithmic improvement. What we have is now a Turing machine, a one-tape Turing machine, which runs asymptotically faster than our previous Turing machine. So this Turing machine is inherently better, or we would say it's inherently better than the previous Turing machine. Why is it better? Both of them are solving the same problem, but one of them is doing it in order n squared, and the other one is doing it in order n log n. So asymptotically, or when n is large, the second Turing machine is taking a lot less time than the first Turing machine, and therefore it is a better Turing machine. You must have studied sorting algorithms in your algorithms course, and you must have studied bubble sort, which takes order n squared time to sort n numbers. On the other hand, you must have studied merge sort, which takes order n log n time to sort its input. Therefore, we prefer merge sort over bubble sort because merge sort is a much faster algorithm. So in this case, we have seen an example where a one-tape Turing machine takes time order n squared to solve one problem, and another one-tape Turing machine takes less time to solve the problem. And complexity theory says it measures these two algorithms or Turing machines and tells us which one is better. Computability theory had nothing to say about these two Turing machines. It would have just said that both these Turing machines show that the problem is decidable. Complexity theory is having a much closer look at the algorithms. Let's now define complexity classes. Let T be a function which maps natural numbers to natural numbers. We define the complexity class time of Tn. Time of Tn is the collection of all those languages that are decided by order Tn time Turing machines. In this case, when we are saying order Tn time Turing machines, we are actually saying order Tn time one-tape Turing machines. Let's look at more closely what we have defined. So for example, time n is the set of all languages L for which there is a linear time single-tape Turing machine that accepts L. Time n squared is the set of all languages L for which there is a quadratic time Turing machine that accepts L. Similarly, time n log n would be the set of all languages for which we have a Turing machine that runs in time order n log n and accepts those languages. So what we are doing is we are collecting languages according to how difficult it is to solve them. So time Tn collects all languages, all possible languages that can be solved on a single tape Turing machine in order T of n time. Let's recall our previous example A, which is 0 to the k, 1 to the k, a set of all strings of that form where k is greater than or equal to 0. The first algorithm showed us that A is an element of time n squared. The second algorithm showed that A is an element of time n log n. Well, there's no contradiction here because time n log n is contained in time n squared. But this example shows that this language belongs to time n log n, so that is a better upper bound, better way of classifying this problem. Now, what would happen if we were to allow ourselves to have a two-tape Turing machine? So let's ask this question, what will happen if we were to allow ourselves 2 tapes instead of 1 tape, or 3 tape instead of 1 tapes? Well, let's recall a study of computability theory. What we proved was a very interesting theorem. We said that if you give me a multi-tape Turing machine, for every multi-tape Turing machine there is an equivalent 1-tape Turing machine. So in some sense, adding tapes to a Turing machine does not improve its computational power. Whatever can be decided by 50-tape Turing machines can also be decided by a single-tape Turing machine. However, now we are asking a different question. We are saying, is it possible to use 2 tapes and solve a problem more efficiently? Well, let's think about the problem that we have already solved, and let's see a simple 2-tape Turing machine for it. What this Turing machine does, remember it has 2 tapes. First, it scans across and finds out all zeros, if all zeros appear before all ones. Then it makes another pass over its input and copies all the zeros to the second tape. Now it scans the first tape in the forward direction and second tape in the reverse direction, crossing off each zero with a matching 1. If all the zeros and ones are crossed off, it accepts, otherwise it rejects. So this Turing machine is very simple. It gets a strings of zeros followed by strings of ones. It can check whether it's in that format, otherwise reject. Then it copies the zeros down onto another tape, and then it moves this head backwards and this one forwards, matching off the zeros with the ones and seeing if all of them can be crossed off by matching them and crossing 1 0 and crossing 1 1. So it can recognize this language in linear time, in order 1 time. In fact, if you're a bit clever, you can design a 2-tape Turing machine which can recognize this language and only scan its input exactly once. For that you have to be a bit clever, but it's not hard to see that you can easily do this in order n time. Thus, we have a 2-tape Turing machine that recognizes this language A in order n time. We had a 1-tape Turing machine which recognized this language in order n squared. Then we made a better 1-tape Turing machine that recognizes this language in order n log n. And now we have made a 2-tape Turing machine that recognizes this language in order n time. This leads us to an extremely important and interesting question. So the question is, can we design a 1-tape Turing machine which strictly improves the upper bound that we already have? We know that we have an algorithm, a single-tape Turing machine that solves this problem in order n log n time. We have a 2-tape Turing machine that does it in order n time. Order n is little o of n log n. So we can ask if there is a single tape Turing machine that can solve this problem in little o of n log n time? Or even more importantly and interestingly, can we actually make a single tape Turing machine which will recognize this language in order n time? That would be wonderful. However, the answer to this question is no. Any single tape Turing machine that recognizes this language A requires order n log n time. In fact, a lot more is known. It is known that there is a language L such that L is accepted by a two-tape Turing machine in time order n. However, L cannot be accepted by any one-tape Turing machine in time little o of n squared. Such examples show how we cannot improve the following theorem in general. So, the example of a language which can be recognized in time order n on a two-tape Turing machine but must require time order n squared on a single tape Turing machine shows that this model with a single tape and a two-tape Turing machine is slightly different from each other when we also look at the time required by these algorithms. Thus, the definition of time Tn changes if we talk about a one-tape Tm or a two-tape Tm. Fortunately, it does not change by too much, as the following theorem shows. The theorem says that let Tn be a function which is larger than n, so Tn is greater than or equal to n, then every Tn time k-tape Turing machine has an equivalent order t squared of n single tape Tm. So, what is this theorem says is, suppose you have a Turing machine which uses k-tapes and runs in time Tn. What you can do is you can make a new Turing machine which has a single tape, and that Turing machine will recognize exactly the same language as the k-tape Turing machine. However, this Turing machine will now operate in time order t squared of n. So, at the cost of a quadratic blow-up, you can eliminate the k-tapes and reduce them to a single tape. Let's compare this theorem with an analog. We proved an analog of this theorem in computability theory. Let's look at that theorem. We previously proved that every k-tape Turing machine has an equivalent one-tape Turing machine. Notice that we were ignoring time, and now we are doing a much more detailed analysis. What we are saying is, if we try to remove k-tapes and convert a k-tape Turing machine to a single tape Turing machine, do we have any penalty to pay in terms of time? Well, the theorem says that the penalty is not too much. What you do is in the worst case, you square the time. Let's start by looking at a proof of this theorem. The proof of this theorem is just a more careful study of the previous proof. Remember, in the proof that we did in computability theory, what we did was we took a k-tape Turing machine and we looked at it and we developed a one-tape Turing machine that simulates this k-tape Turing machine. How does it do that? It first takes an input x and writes down the initial configuration on its tape. So it writes down Q0 followed by x, and that's what's written on the first tape, and all the other tapes are blanks. Then it makes passes over this configuration, and in each pass it converts the configuration into the next configuration. And since we can build the transition function of the k-tape Turing machine inside the one-tape Turing machine, it can keep converting the current configuration into the next configuration. And this way, the one-tape Turing machine simulates the k-tape Turing machine. If it ever reaches an accepting configuration, it accepts. If it ever reaches a rejecting configuration, it rejects. We said that now we had an equivalent one-tape Turing machine. Now what we want to do is we want to see how much time does this simulation take. So let's look at this Turing machine more closely. On input x, convert the input to hash q naught x followed by hash sign as many as there are tapes. This is the starting configuration of M. This configuration says that the X is placed on the first tape and this state is Q naught and the rest of the tapes are empty. Make passes over this tape and change the current configuration to the next one. If an accepting configuration is reached, accept. If a rejecting configuration is reached, reject. Now what we want to do is we want to estimate how much time does this new Turing machine N requires. So what we want to do is we want to ask the question, what is the cost of doing this simulation in terms of time? And of course, we will be able to say something meaningful in terms of upper bounding the time required by this single tape Turing machine. Let's see. Suppose that we give an input of length n to this Turing machine. First observation is that our original Turing machine uses at most Tn cells of its k tapes. Why is that? Well, any Turing machine that runs in time Tn can use at most Tn cells of any of its tapes, because even if it moves its head to the right every time, it will only go Tn steps further. So we know that M uses at most Tn cells of each tape. From this we conclude that any configuration is going to have length at most k times Tn, which is order Tn. So the length of any configuration is going to be order Tn, not more than that. That's our second observation. The third observation is this means that each pass that this new Turing machine N makes over its single tape will require at most order Tn steps. This single tape Turing machine just makes one pass over the whole configuration. The configuration has length order Tn, so each pass of the single tape Turing machine will require order Tn time. Our last observation is that N makes at most Tn passes on its tape. After that, M must halt. This is because we know that M runs in time Tn. After Tn steps on an input of length n, M halts. So this Turing machine will make at most Tn passes. Each pass is requiring order Tn time. So the total time required would be order T squared of n. So this shows that n runs in time order Tn times Tn, which is order T squared of n. Here I want to ask you one very simple question. Where did we use the fact that Tn was greater than or equal to n? Whenever you have a theorem and it has a hypothesis, you must use all the things that you had in the hypothesis in order to prove that theorem. Because if there's a particular hypothesis that you did not use, then you could have removed that hypothesis from the theorem and proved a stronger theorem. So implicitly I have used at one place that Tn is greater than or equal to n, but did not tell you. So let's now identify where we have done that. Well, remember the first step. The machine converts x to the initial configuration, and this takes time order n. Thus the total time was actually order n plus order t squared of n. Since t of n is greater than or equal to n, therefore we can ignore the order n term and the total time is order t squared of n. The assumption that t of n is greater than or equal to n is actually a very reasonable assumption, because think about a Turing machine that takes time less than n. Well, that means it does not read its entire input. It doesn't have enough time to read its entire input. So this assumption is actually true for many problems, many problems. The decision whether the string is in the language or not in the language requires us to read the whole strings. For all those languages, this assumption will be true, and therefore this extra assumption that t of n is greater than or equal to n is not an unreasonable hypothesis to make. It actually captures many problems, many Turing machines, and there are only a few k-tape Turing machines for which this theorem is not applicable, and those are not solving very interesting questions. Well, now we will move on to a new topic, which is going to be non-deterministic Turing machines. You have studied many non-deterministic models in your automata course. For example, you have studied non-deterministic finite automata, NFAs as you call them, and you proved that NFAs were equivalent to DFAs. In fact, the study of NFA is extremely fruitful in automata theory. It helps us in proving many closure properties of regular languages. Then you also studied push-down automata, and you were told and you proved that push-down automata capture context-free grammars, but only if you allow non-deterministic push-down automata. So that was another model of computation that you studied. Non-determinism is an extremely important concept in computer science. What we are going to do is now define non-deterministic Turing machines. Well, you will recall that non-deterministic finite automata was in a given state, and when it reads the input, it has choices. It can go to one state or another state. So the transition function for a non-deterministic finite automata delta of q comma a is actually a set. Those are the next possible moves that it can make. Non-deterministic Turing machines are also like that. A non-deterministic Turing machine is in some configuration, and the next possible move is not one, but several of them. And in some sense, it makes all those moves together. Well, let's look at the formal definition of what a non-deterministic Turing machine is. A non-deterministic TM formally will be given by, once again, sigma, gamma, q naught, q accept, q reject, and the transition function delta. Once again, sigma is going to be the input alphabet as usual. Gamma is going to be the work alphabet. There's going to be a set of states q, and q naught, qa, qr are going to be the starting, accepting, and rejecting states. The difference is in the transition function. Delta, the transition function, now maps q cross gamma to the power set of q cross gamma cross LR. Previously, what a Turing machine does is it reads an input, so it takes a symbol q, a state q, and it reads something from the work alphabet and decides to make a move. And that move is to move into a new state, replace that symbol, and move either left or right. Well, a non-deterministic Turing machine can make several moves. It has several possible next moves. Therefore, delta is not mapping to q cross gamma cross L comma R, but the power set of it. So delta of q comma a is going to be a set of next possible moves. Let's look at an example. So we may have delta of q5 comma a to be the set q7br, q4cl, q3ar. What this means is that if the machine is in state q5 and it's reading an a, it can either go to q7 and write a b and move to the right, or go to q4, write a c and move to the left, or it can go to q3, replace the a with the a and move to the right. Thus, this machine has many possible ways to proceed. When we give a non-deterministic Turing machine an input, well, it is in the initial configuration, and it has several possible next configurations. So we can think of its computation as a large tree. From the initial configuration, it goes in one step to several others. So the initial configuration is the root of this tree, and the next configurations are children of this tree. And then from all those configurations, there are several possibilities. So we can examine the computation tree of a non-deterministic Turing machine. Here on the screen, you can see how this tree models a computation of a non-deterministic Turing machine. Well, if the computation is a tree, we have to decide what does it mean when the Turing machine, this non-deterministic Turing machine, accepts an input. The answer is, we'll say that X is accepted by this input if there is at least one branch of this tree which accepts the input. So we will say that X is rejected by a non-deterministic Turing machine if all branches reject. So remember, there is an asymmetry in acceptance rejection criteria here. We say that X is accepted if at least one branch in the computation tree accepts, and we say that X is rejected if all branches reject. Well, how will we define the running time of a non-deterministic Turing machine M? Remember that its computation is described by a computation tree. So the running time will be the depth of this tree, the length of the longest branch. More formally, the running time of a non-deterministic Turing machine M is the function f such that fn is the maximum number of steps M uses on any branch of its computation on any input of length n. So if I say that a non-deterministic Turing machine runs in order n squared, that means if you give it any input of length n, in the computation tree, all branches will have length less than or equal to order n squared. If, on the other hand, if I say that the non-deterministic Turing machine is taking order n cubed time, that means if you give it any input of length n, the longest branch that you will have on any computation branch that you take will have length order n cubed. Let us make a few comments about this definition. The notion of non-deterministic time does not correspond to any real-world notion of a machine we can make. So, in some sense, non-deterministic time is not a practical way of describing time taken by Turing machines. It does not correspond to any practical model that you can make. We cannot make non-deterministic Turing machines. However, it is a very mathematical concept, and it's going to try to capture some essential problems. So, you should think of it as merely a mathematical definition. We will later on see that this definition is extremely useful. It allows us to capture many interesting problems. So, non-deterministic time is not a practical notion. However, it is extremely useful in capturing problems. This point will become clear as the course goes along. Let's prove some relation between non-deterministic time and deterministic time. Let's say that Tn is a function and we have a Tn time running non-deterministic Turing machine. What we will prove is we can make another Turing machine which is deterministic, a single tape deterministic Turing machine that is equivalent to the non-deterministic Turing machine and runs in time 2 to the order Tn. What this theorem says is that we can get rid of non-determinism at the cost of exponential blow-up in terms of time. Thus, if you have a non-deterministic Turing machine, you want to convert it into a deterministic one, you can do that, and the cost of it would be no worse than an exponential blow-up. Let's prove this theorem. Let n be a non-deterministic Turing machine that runs in time Tn. Let us first estimate how big the computation tree of n can be. The first point to notice is that the tree has depth Tn. Let b be the number of legal choices, maximum number of legal choices given by n's transition function. Then this tree can have at most b to the Tn leaves. Thus, the total number of nodes in this tree can be at most 2 times b to the Tn. It's actually given by that geometric series that is written on your screen, and if you sum up that geometric series, it's easy to see that the answer is less than or equal to 2 times b to the tn. So this computation tree is of size b to the tn. So the size of this computation tree is order 2 to the order tn. Well, the rough idea is we will make a deterministic Turing machine that will painstakingly go through this computation tree, one node at each time. And what we will show is that this Turing machine does not incur a very large overhead. Thus, all it has to do is visit all the nodes of this computation tree, and once it's done that, it will know whether the non-deterministic Turing machine is accepting its input, if it ever hits an accepting configuration, or whether all the branches are rejecting its input. This way, our deterministic Turing machine will take time 2 to the order tn. The deterministic Turing machine that we make is going to be a k-tape Turing machine. It's going to have more than one tape. It'll be easy for us to construct the single tape Turing machine that way. Once we have done that, we will use our previous theorem to convert that into a single tape Turing machine. Well, we will examine the details of this proof in the next lecture. I'll see you next time. Thank you and goodbye.